Okay, let's continue. So we discuss force between force, the magnetic field in a straight wire, and then how these magnetic fields interact with other nearby wires and how they create force and all that. So let's move on. We talk about this, the definition of electric current, the ampere. Alright, so let's take a look at some applications. Now let's go back to what we discussed earlier. If it is a straight wire, a single wire, and take the current as I, the magnetic field, when there's a current in a conductor, it creates a magnetic field. Now this is the most simplest electromagnet we can think of, right? Just a wire and there's current through it. So the magnetic field at a given point, let's say over here at this point, distance r, B is given by mu naught I over 2 pi r. Now at this distance, at any point, any of these points will have the same magnetic field. On the other side also, over here, if it is the same distance, the magnetic field will be same. If you measure it a little closer, it will be bigger. If you measure it further away, it will be smaller. So this is just a single wire. Now you take this wire and you make a coil out of it. So you bend the wire into a circle. So this is the wire, you bend it into a circle, like a couple of circles. Something like this is called a solenoid. If you look at the diagram to the side, here we have a solenoid probably like this. So when there's current flow, current goes in, makes circles inside this. So in these circles, like if you look at it from the side, let's say you're looking at this is the eye, this is the human eye. You're looking, you're looking at it from the side, what you see is a circle, bunch of circles like this. In one side the current turning, like going in, you can say the other side it's coming out. So if you look at these individual loops, in each loop, when you're looking at it from where you are sitting right now in front of the computer, all these top loops, top side, you can say the current is coming towards you, these circles right over here, it's coming towards you. In the bottom, the current has to go away from you, crosses. So that's what this diagram explains, right? Current is coming out of the page, going into the page in these several loops. Now, doing some calculations, we can figure out the total magnetic field it creates. We're not going to discuss, we're not going to get into all the math, but we're just going to go to the final equation. So a straight wire, a single wire, you make a single loop out of it like this. So it is so the magnetic field created by this, each little segments, it adds up. So the magnetic field inside this loop, it's a summation of all the little magnetic fields created by these little segments, right? Using calculus we can do that. At this level we're not gonna get into the math. Okay, and then you have a couple of those, several loops like that. So all together, what is the magnetic field inside the solenoid? It's given by magnetic field is mu naught n I. This is the permeability. We already know that. T number of loops per unit length. This is the current, right? So higher the permeability of the material means medium. Now if the coil is just something like this, if there's nothing inside, if it is just an air inside, empty one, so it's the permeability of air. Number of loops per length. Let's say this coil is 20 centimeters long from one end to the other, and there's, let's say, 2000 loops. So loops per unit length, so that will be, n will be 2000 divided by, it's a little too much, let's say 200 loops. 200 divided by 0.2, so what do you get? 1000, right? 2000 divided by 200, yeah, 1000 loops per length. Okay, so that's that, and the current through it. So if we put this thing in another medium, like put some different permeability inside, we can increase the magnetic field, strength of the magnetic field. If you put more loops, if you wrap them very tighter, close to each other, you can increase the magnetic field. If you put more current in it, then you get higher magnetic field. So solenoids are very useful, a very practical application. So let's see what next slide is. Let's go back. So when there's current, this acts like a bar magnet, right? So it is like a bar magnet, north and south. I'll tell you later how to determine the poles of this. So the current is going in, current is coming out. So for a bar magnet, we know that the magnetic field lines coming out from the north pole, going into the south pole, the field lines around it. Same thing here. There will be magnetic field line coming out, going into the south pole. Advantages. First of all, you can control the magnetic field. More current, more magnetic field. You can change the direction of the magnetic field. If you switch the current, if you change the direction of the current, you can switch the direction of the magnetic field. You can turn it on and off. If it is a permanent magnet, you can't turn it off. It's always there. But an electromagnet, you can control it very easily. Just attach a switch. You can turn off the magnetic field. So you can change the magnitude, you can change the direction, you can turn it on and off. Plus, inside, within the coil, in the coil space, there's very uniform, straight, strong magnetic field lines, which we can't attain with permanent magnets like bar magnets, because inside, even though there's a magnetic field, we can't do anything, right? It's inside the material. All we can do is use the magnetic field exist outside. But here, let's say you want to test some biological sample for its magnetic properties, and you need a really uniform magnetic field. You make a big coil like this, place the sample inside. So there's so many applications like that. Okay, so let's try an example. Alright, let's give it a try. Calculate the field inside near the center. So this calculation works through this center axis, right? So if it is a very thin coil, doesn't have much thickness, yes, you can say that is the that is uniform throughout. But if it's a large coil, the numbers work for the magnetic field right along the axis. Either way, let's find the answer. B equals 1 naught and I 4 pi 10 to the -7. 400 turns per 10 centimeters. So N is 400 over 0.1. current is 2 amperes. So let's do the math, see what we get. So I have something like 5309 times 10 to the negative 7. 1, 2, 3, 4, 5. 1.005 10 to the negative 2 units Tesla. Okay, so these kind of things are called solenoids, right? A coil or like a linear coil. Now, there's another application. You take the coil and you bend it into a circle. So it looks like kind of difficult to draw unless you're good at drawings. This is called a toroid. Again, we're not going to get into calculations with toroids. Just I want you to see what it looks like. It has unique applications, can make much stronger magnetic fields. This is a self-study part, so read up about this. I want you to know some applications of solenoids and toroids. Okay, solenoids and toroids, self-study. Don't worry about the equation for the toroid, just find out some conceptual information. Okay, moving on. So the rest is mostly conceptual stuff. Magnetic materials. What kind of materials can become magnets that we can make magnets out of them? We call them ferromagnetic materials. Examples are iron and nickel, I think cobalt also, and their combinations, different compounds. So all this is a self-study. More about ferromagnetism. Here's a picture, a sketch of what is inside. Like these are the little domains. You see that in the first picture they are not aligned, they are in random directions. The second picture they are a little bit more aligned, actually really not. Yeah, but using an external magnetic field we can align all these arrows in one direction, and ferromagnets can hold that alignment without changing it. So that's why we call them ferromagnetic. They can hold on to that alignment, so they act like a magnet even if you remove that external field. So you can make permanent magnets. You can destroy a permanent magnet by heating it up. Temperature can mess up these alignments. The atomic vibrations can change these alignments. If you drop the magnet, that vibration can mess up this alignment. Okay, that's ferromagnets. Moving on. Here's a solenoid. So here the current comes in, make a couple of rounds, comes out, and here's the way to figure out which side is going to be the north pole. Now take the right hand, go to the first right hand rule, bend the fingers and extend the thumb outwards. In this case, place your 4 fingers in the direction of current is rotating. So if you look at this, you see that the way the current rotates, you have to place your fingers pointing to you, to yourself, right? And the thumb, that way the thumb points to the right. So it is something like this. So this is your right hand. Okay, this is without bending the fingers. And now you're going to bend these fingers. This is the little finger, this is the ring finger, this is the middle finger, this is the index finger. They're all like this. And thumb pointing outwards. So if you look at this coil, again I can show this in class much better. So when the current rotates in this thing, it's like current coming to you from the top, going away from you from the bottom. So when you place your hand to match this alignment, the only option is thumb pointing to the right, and that tells you the magnetic field is pointing to the right, making a north pole here and a south pole here. Okay. All right. These things I will explain in class on video. That it will make much more sense than trying to drawing these things. Here's some simple applications. Nowadays you don't see these things anymore because all these doorbells and all that are electronic. But this is what the old-fashioned thing looked like. So when you turn the switch on, there's a coil here. There is a coil here. The coil gets magnetized. It's gonna pull this iron rod because it's a magnet. It can attract iron. So it's gonna pull this iron rod towards it, and it will hit the bell, make sound. You let the switch go, it breaks the current. No more current means no more magnetism. So the iron rod will go back because of the spring action. And a simple way of this is something you can build at home also. You can find a piece of conductor like a copper wire, make a couple of coils out of it, maybe I would say 100 turns. Connect it to a battery, get like 3-4 1.5 volt batteries, more the better, like I would say 3-4 should do it. Connect it and you see that this little coil can attract metal iron stuff. That's an electromagnet. Paramagnetism and diamagnetism. So all these self-study, I'm just very briefly going over these. All materials exhibit some level of magnetic behavior. Most are either paramagnetic. Mu, that's permeability, slightly greater than mu naught, permeability of free space. So paramagnetic materials will have little higher permeability than air. Diamagnetic has permeabilities little less than that. Ferromagnetism will have higher permeabilities. Alright. So here's some examples. So going back to this solenoid example, this coil example. So let's say you make a coil like this, connect this to a battery, you can put a switch, and by turning it on and off, you have this electromagnet, right? So let's say current flows through it in such a way that this side becomes a north pole and this side becomes a south pole. Now, if you put some material inside, most of the time these coils have some core within it. Usually it's an iron core. Iron is a good ferromagnetic material. Having some ferromagnet inside the coil actually improves the strength of this electromagnet. So when the coil becomes magnetized, it's going to align these domains in the piece of iron also. So it kind of adds up and becomes a stronger magnet. So this will be a stronger magnet than just having the same coil without anything inside, right? Same way with paramagnetic materials like aluminum, calcium kind of stuff, you can increase the magnetic field a little bit, not a lot, but a little bit. Interestingly, diamagnetic substance, if you apply an external magnetic field, the total decreases. Diamagnetics actually work the opposite way. So this ratio, it's found permeability divided by the permeability of space minus 1 is called the magnetic susceptibility. We don't need any of these. Just, you can become familiar with the terms. That's useful. But that's the idea. So I want you to read up about these two types of magnetisms as well. Okay? Alright, let's move on. I'll leave the slide for you to read. Okay, here's the summary of what we discussed. This is for a straight single wire solenoid, and that's it. Alright, thanks.